So, from this session we will be discussing about the core departmental subject which is exclusive to chemical engineering, that is mass transfer or separation. You see, in basic level this is a fundamental subject, and the principles of this subject actually we use to design and simulate to control the different central equipments of a process plant like distillation column, absorption tower, then cooling tower, drying chambers, then leaching units, filtration or not the conventional filtration unit, the membrane filtration unit, the chromatographic separations and many others. So, here in mass transfer, fundamentally just like heat transfer, we have started with conduction or diffusive transport of heat. Here in mass transfer also we will be fundamentally discussing about, we will initiate our discussion about the molecular diffusion processes, right. Now, you may immediately try to point out that what is the utility of this diffusion process, because there are generally two types of mass transport. First one is diffusive transport and the second one is the convective transport, right. Unlike radiation, which is definitely not possible in this mass transport, right, what we have in heat transport without any medium. So, here most of the industrial units they operate with convective transport mode. However, very close to that interface, right, specifically when we are having a solid interface at which the velocity is 0, at the interface the velocity is 0. So, over this region the degree or the effect of turbulence, right, it is pretty negligible, and all these units actually operates in molecular diffusive regime very close to that solid interface. Like in a packed bed or packed tower, we have these packing materials which are static, and on the surface of that we have 0 velocity of the gas and the liquid. So, close to that interface, and even for this catalyst and many other operations, we have the role of diffusive transport. And diffusive transport is fundamentally important from this theoretical perspective, in a sense that first we try to understand the subject's basis from the historical point of view, that initially we have these diffusive transport formulations and that we extend to get a working equation in these convective domains, right. Definitely there are some empiricity we have to incorporate in, because the turbulence as a whole is still not very well understood or cannot be reduced into a simple working equation when we are dealing with simultaneous mass transfer, right. So, for this purpose we have to rely on empiricity and empirically develop different equations we have to use. So, today we will be majorly focusing on diffusive transport, and therefrom we will try to understand that how these basic equations of this diffusive transport are bit modified and semi empirically extended to get the working equation in convective domains. So, before we start this diffusive transport, let us understand some notions or notations what we use to represent the concentration and therefrom the velocity, and from there we will try to get these basics of this Fick's law. So, you see that concentration we can represent as mass concentration rho I, that is in kg per meter cube. So, obviously the average concentration, if it is a multi-component system, is equal to rho, and that is summation of rho I, right, and mass fraction Wi we represent as rho I divided by rho. And similar to that, we have molar concentration. Ci mole per meter cube, this average concentration, or rather than not the average concentration, we should say it is the bulk concentration, right. So, this is also bulk concentration. C, that summation of Ci, and mole fraction, we write Yi or Xi based on, this is for gas phase, this is for liquid phase, and that is Ci divided by C. So, once we have defined the notations what we use for represent this concentration, next we will discuss what will be the, how to represent the velocity, right. Now, here the velocity indicates that individual molecular velocity as well as bulk velocity, and this we refer as average velocity, right. So, whenever in a multi-component system individual species they moves, the velocity definitely will be different because there are diffusive aspects of one component with respect to the other, right. So, individual molecular velocity we will write it as Ui, and regarding average velocity, this is the bulk velocity basically. So, here we can define two different velocities based on with which we are weighing Ui, right. It is a weighted average. So, we can weigh it with rho I, we can weigh it alternatively by Ci. So, we have first mass average velocity, which is say small u, and that is equal to Ui rho I divided by rho. And second one is molar average velocity, capital U, which is small ui Ci divided by C, right. So, we have defined two different average velocities, and this average velocity, you see this what this Ui rho I actually represent. This represents the respective mass flux, right, because the density or this mass concentration, not the density, the mass concentration is being represented as kg per meter cube, right. So, this term if you do a unit analysis or dimensional analysis, kg per meter cube multiplied by meter per second, right. So, it gives you kg into meter square per second. So, obviously, it is a mass flux because transport of mass per unit area per unit time, whereas here it is meter per second into mole per meter cube giving you molar flux. Now, you see that bulk motion or the average velocity, if we see it as it is caused by some macroscopic driving forces like pressure difference or difference of gravity, gravitational head, etc. right. So, majorly these two. So, these are the major driving forces to trigger the bulk motion of that fluid. However, we have individual molecular velocity which is actually being triggered by these microscopic forces, right. So, diffusion, why the diffusion takes place actually? Because the diffusive motion actually is to maximize the entropy and to homogenize the concentration. So, it is a molecular aspect whatever is interplaying as a fundamental root cause of diffusion, right. So, we have the individual molecular velocity. It may not be diffusion only, it is the individual molecular velocity, right, which we look from a reference frame that is static. But if I move with average velocity, I will see only the diffusion of that specific component. Okay. So, try to understand, we have a bulk motion. We have a bulk motion. Now, we see it with respect to a static reference frame. So, what we will observe? An individual molecule is moving with velocity uy, right. Individually it is moving with velocity uy. Now, we can have two different other reference frames. One is moving with molar average velocity, another is moving with mass average velocity. So, with respect to that, when we see this, so it becomes a different type of velocity, rather it is, we should say that it is a kind of diffusive velocity, right. So, we represent the mass flux with respect to number 1, a static reference frame. So, we get Ni equal to rho I uy, what I have written previously here. Next, with respect to with respect to I have already written a reference frame that is moving with mass average velocity. Right? What notation I have used? Yeah, II. It is rho I into ui minus u. Now, also we can define reference frame that is moving with molar average velocity. So, it is J I rho I ui minus capital U. Now, what we can observe here, this is mass average velocity, this is the absolute velocity with respect to a static reference frame. However, here we are subtracting the velocity, molecular velocity of a component I from the molar average velocity, and that we are multiplying with the mass concentration. So, this definition with inconsistent is basically inconsistent with rho I. So, this specific mass flux expression we do not use that much, right. So, either we use this or we use this. So, similar to this mass flux, we can also define the molar flux, right. We can also define the molar flux. And how we can define it? Molar flux with respect to number 1, static reference frame, capital Ni, which is Ci into Ui, right. With respect to a reference frame that is moving with mass average velocity. So, we have capital II equal to Ci ui minus capital U, and third, reference frame that is moving with molar average velocity. Capital Ji this is small u, this is capital U, right. So, this small ui minus capital U, sometime we alternatively refer it as diffusive velocity, because this velocity is entirely contributed by diffusive characteristic of that specific component, right. So, diffusion velocity we may define V di as, how it is defined? It is defined as ui minus capital U, right. So, this is the diffusive velocity with respect to the molar basis, and that is more fundamental because the Fick's law is written in terms of molar concentration, right. So, generally we express it not in terms of rho, but in terms of C, the concentration itself. So, we have these basic ideas, and from there we will try to move to Fick's law. And again you note that this is again inconsistent, similar to this. Why? Because here we are subtracting the velocity from this mass average velocity and multiplying it by the molar concentration. So, this is mass average where this is molar concentration. So, they are not consistent. So, that is why we do not use majorly II. So, we are going to now, whatever theory we are trying to develop, we will be mostly focusing on this molar flux with respect to the static reference frame and the molar flux with respect to a reference frame moving with molar average velocity. So, with this basic understanding, let us go to Fick's law. So, you see Fick's law represents Ji, right. So, Ji what we have done or what we have actually defined, so it is Ci ui minus u, right. So, diffusive molar flux. So, this is the diffusive molar flux, and according to Fick's law, this diffusive molar flux is proportional to the concentration gradient, respective concentration gradient. So, Ji is proportional to grad of Ci with a minus sign. It is of course basically it is the same logic what we can apply in case of Fourier's law or Newton's law of viscosity. So, Ji is becoming minus of di grad Ci. So, Ji is also a vector, right. So, di is the diffusivity of I in the medium, and grad operator, as you all know, that in Cartesian coordinate we can write it like this. In cylindrical and in spherical coordinate it will change its form. So, Ji x in scalar form di into del Ci del x, Ji y minus of di del ci del y and ji z minus of di del ci del z. So, these are the respective scalar form. Now, this sort of equation, this Fick's law cannot be theoretically proved, right. At least within our classical domain of understanding, it cannot be theoretically proved. It is an outcome of observation. So, this Fick's law is alternatively belongs to a class of equation which is called phenomenological equations, right. And this di, the constant, is the phenomenological coefficients, right. So, you see, phenomenology means actually you are trying to relate the cause and effect. The heterogeneity in concentration field is the cause and the flux is the effect, the diffusion is the effect. Okay. So, this is the cause, this is the effect, and they are relating the cause effect through a kind of proportionality, and the constant of this proportionality we refer it as the phenomenological coefficient in general, and in particular that is the diffusivity for this specific case. So, we can actually get the unit of diffusivity. See, Ji, this is represented as we have discussed mole per meter square second. Now, grad of concentration, it is mole per meter cube into 1 by meter, right. So, mole per meter square second is equal to di into mole per meter to the power 4. So, obviously, we get that di is meter square second, or in general L square t to the power minus 1, right. So, in SI its unit will be meter square per second and its dimension will be L square t to the power minus 1, where L and t represents the length and time dimensions individually. Okay. Now, we will focus from this general understanding of the Fick's law. Now, we will try to relate this, or we will try to actually simplify some relations between J's in case of a binary system. Majorly, we will be concentrating on this binary solution, where we have two components A and B. So, I is not being represented as 1 or 2, it is A and B. So, if I have two components, you see JA is minus of DAB, diffusivity of A in a solution of A and B or through B, into grad of CA, and JB D of BA grad of CB, right. Alternatively, it is CA into UA minus capital U, and this is CB into UB minus capital U, right. So, this we can write as U, these are vectors. So, NA, because CA into UA must be equal to NA minus CA into U, and this is NB minus CB into U, right. So, from here we can get that NA is equal to CA into U minus DAB into grad of CA, right, and NB we can also write as CB into U minus DBA into grad of CB, right. Now, you see that U, if I replace the basic definition, it becomes CA by C within bracket CA UA plus CB UB. So, here we will write this Na plus Nb. Because if you follow the definition of capital U, what we have written previously, it was summation of Ci Ui divided by summation of Ci, which is C, right, the bulk concentration, minus dAb into grad of Ca, and Nb is equal to Cb by C Na plus Nb minus dBA grad of Cb. Now, if you add these two equations here, we will get what? This will cancel out, these two terms and these two terms will cancel out, because Ca plus Cb equal to C, right. So, 0 equal to minus of dAb grad Ca minus of dBA grad Cb, right. Now, Ca plus Cb equal to C, which is constant. So, grad of Ca is equal to minus of grad of Cb. So, if I take this grad of Ca out with a minus sign included, so dAb minus dBA. Now, grad of Ca for a diffusive process can never be equal to 0. So, grad of Ca is never be equal to a null vector under 0. So, dAb equal to dBA. So, diffusivity of A in B is same as that of the diffusivity of B in A, right. So, we have got these basic expressions. Now, if the bulk motion itself is absent, right, if the bulk motion is 0, we have only diffusive transport, then definitely Na is equal to Ja, right. So, in case of pure diffusive process, Na equal to Ja equal to minus of dAb into grad of Ca, right. And you see that diffusion velocity VAD, the diffusion velocity, we can write it as U minus UA, right. U minus UA, or rather sorry, just the opposite, UA minus U, and UA can be expressed as UA minus U. So, it is Ja by Ca, it is dAb by Ca into grad of Ca. It is obvious outcome. Now, sometimes you say instead of concentration, we use partial pressure because it is directly measurable for gases. We use partial pressure for gas mixture, and Ca, you see from the ideal gas law, PV equal to NIRT, or rather Pi is equal to NIRT, that is a definition. So, Pi divided by RT is equal to Ni by V, which is Ci, right. So, if I replace this, I will get Na is equal to Na plus Nb. Next it was Pa by Ca by C. So, Ca is proportional to Pa, C is proportional to the total pressure according to this equation. So, we can write it Pi divided by P minus dAB into grad of CA. Now, CA if you replace as PA by RT, so we will get dAB divided by RT grad of PA, right. So, that is the equation which we can use in case of gases. So, that is the general analysis of this diffusive process, very similar to conduction in heat transport. Now, in conduction you see from this general conduction equation, we have tried to, or we have from the Fourier's law, we have tried to derive the general conduction equation. So, here we will not do this same, but similar. We will use the convective contribution of transport simultaneously and also the contribution of reaction, right. So, we will get what is referred as convection diffusion reaction equation or sometimes advection diffusion reaction equation. So, we call it convection diffusion reaction equation. In 1D, see, we have a one dimensional transport to simplify the geometry of this case, and this is say x direction, this is x plus delta x, and here we have diffusive transport, we have also the convective transport. So, diffusive transport is Jx, right, of this component what I have written A. So, Jax, and here it is Ca into U or Cax into U, right. So, you see if I combine these two, we are actually getting Nax, because Nax is Jax plus Cax into U, right. So, because this and this, if you write this and check the equation previously what we have written, we will get the same equation. So, basically we are trying to write the molar flux with respect to a static reference frame. So, on this other side at x plus delta x, we have Ca x plus delta x into U, we have J of A x plus delta x. So, and let us say the reaction rate minus Ra, which is defined as minus of 1 by V d, let us say Na reaction dt, right. Rate of consumption of component A by the reaction per unit volume of the reactants. So, that is the volume, V is this, okay. So, we will write a balance equation over here. So, rate of accumulation is area, let us say area is small a, this area is small a. So, small a into delta x into del Ca del T, that is the rate of accumulation. Now, inflow will be Jax into A minus of plus of Cax into U. U is also may be changing, right, from point to point, that is the inflow, minus outflow Jax plus delta x into A plus Cax plus delta x into U, right, and minus of Ra into A into delta x, that is the overall consumption, that is dNA Rx dt over this differential shell, right. So, if I divide this equation by small a into delta x, I get this Jax minus Jax plus delta x divided by delta x, then minus U Cax plus delta x minus Cax by delta x minus of minus Ra. So, now del C A del T, you see minus of del J del X minus U del C A del X minus of minus R A. Now, J A in one dimension is minus of DAB del C A del X. So, if I replace it, I will get del C A del T is equal to DAB into del square C A del X square, and if I add this term or change the side of this term, it will be this plus R A. So, that is the form of convection diffusion equation in one dimension, right. So, this is the convection diffusion equation, reaction equation in 1D. So, you see that this is the convection term, very similar to the convective acceleration term in Navier-Stokes equation. This is the unsteady state term, this is the diffusive term, and this is reaction term, right. So, if I extend it general form to the general form, I get del C A del T plus U grad of C A is equal to DAB grad square C A, U dot grad of C A, then plus R A. So, this is the general convection diffusion reaction equation, right. So, you see that further we can write this left hand side term as material derivative of this into grad square C A plus R A. So, it has got a similarity with Navier-Stokes equation or general energy equation. In Navier-Stokes equation, you see we had rho into del V del T minus of grad P for Newtonian fluid, or we can write as rho into G plus grad of stress tensor, and in general energy equation it is rho Cp del T is equal to this K into grad square T plus Q plus heat generation plus 2 mu d double dot T, that is the viscous dissipation term. Now, you see on the left hand side we have the rate of change of here the momentum, here the concentration, here the thermal energy for a particle, right, because material derivative means it is a Lagrangian derivative and it is basically representing the rate of change of that property, right, some extensive property in that particle. So, here this concentration, right, concentration, some property, it should, I should not be saying that it is an extensive property, it is a property of the particle, right. So, it is the concentration, here we have the momentum, and rho Cp T minus T reference is the energy. So, it is a kind of either mass concentration or momentum concentration. Rho into V is the momentum concentration, because its unit will be kg per meter cube into meter per second. So, kg into meter per second divided by meter cube, if you see it like this, it is the momentum concentration in that particle. Rho Cpt is the energy concentration in the particle, that is in joule per meter cube, right. So, these are the material derivative of these concentrations of different terms, that may be mass, maybe this momentum, maybe the energy. And on the right hand side we have either the growth term or the dissipation term. Like the diffusion, as it is dissipating the concentration through this molecular diffusion process. So, this is the diffusion term, right. So, diffusion term here we can get actually, if I write this in for Newtonian fluid, that is rho g minus grad of P plus mu into grad square V. So, this and this, they are diffusion terms. Right. So, material accumulation, definitely there will be a diffusion, and additionally there will be a growth or generated term or dissipated term. Why I am saying that this is a generated term or dissipated term? Because Ra, it will be either consuming A or it may be generating A, right. If it is a consumption reaction, then Ra will be negative, this Ra will be positive because we have defined minus of Ra, right. So, that is the case. Here you see momentum can be generated by changing the pressure or applying a pressure gradient or applying a gravity. If I have a straight pipe, right, filled with liquid, and if I put it vertically down by gravity, we have the generation of momentum. And alternatively, for a straight pipe, if I apply a pressure on the right hand side and keep the left hand side openings pressure at atmospheric, the momentum will be generated. So, similarly here the Q is the heat generation or dissipation per unit volume of the system, and because of the fluid flow there will be the frictional work which will be finally converting into heat, which is the viscous dissipation term. So, they are either the generated term or the dissipated term. So, we have structurally three equivalent transport equation. One is a transport of mass or mole, another is a transport of momentum, another is a transport of energy, right. And convection diffusion reaction equation falls in the same category of Navier-Stokes equation or general energy equation in case of heat transfer. So, if it is a pure diffusive process, you see, if it is a pure diffusive process, what will happen? This term will be 0 for pure diffusive process, and we have no reaction. So, this reduces to what we refer as the general diffusion equation without reaction, right. So, the same we can also get from the scalar component equation. Next, so with that equation, though we are not going to apply the equation in toto what we did in this conduction, but here we this indirectly or directly we will apply the same equation, and we will try to solve for some steady state diffusion problems. Okay. And in books you see the diffusion after this Fick's law and general diffusion equation what we have derived from convection diffusion reaction equation, right, it is much more generalized. So, what they do, they consider only two cases. One is the diffusion of A, it is a basic model of this binary system diffusion study. First one is the diffusion of A through non-diffusing B, and the second one is diffusion of A through counter diffusing B. Now, question is why these two specific cases are chosen, right. In every mass transfer book you will see that there are only two cases they are describing, and they are deriving the here we consider it mostly a gas diffusion. So, in terms of partial pressure we derive this partial pressure profiles, right, for this specific case of binary diffusion. So, why we have chosen these two only? Why it is only counter diffusion equimolar again, and why it is the diffusion of A through non-diffusing B? See, all this mass exchanger we can finally reduce into either one of these two diffusive process to happen. Like in absorption, think we are taking away carbon dioxide, right, a carbon dioxide and air is there, and air is an inert carrier. We are absorbing carbon dioxide in a solvent, right. The solvent is liquid, okay. And the solvent may be some alkaline solvent, say NaOH, or maybe tertiary amines or anything, where the carbon dioxide will be absorbed and air will not, right. Air is practically immiscible in that liquid. So, what will happen at the interface between this liquid and the gas? Only carbon dioxide will diffuse towards the interface, get dissolved, and will further diffuse towards the bulk of the liquid, right. So, it is a diffusion of carbon dioxide through non-diffusing air, okay. Just at the interface, if you look, absorption of CO2 from air in a liquid solvent, tertiary amine or NaOH solution, whatever. So, here we have the interface, this is liquid, this is gas. So, here we have carbon dioxide and air. So, CO2 only will diffuse to the interface, get dissolved, and further it will diffuse into the bulk of the liquid, but air will not, right. So, it is a diffusion of diffusion of CO2, which we call, let us say, A, through non-diffusive B, non-diffusive air, which is B, right. So, think of, in addition to absorption, you think of this cooling tower operation, where we have a hot water delivered at the top of the tower and it flows down, exchanges heat as well as mass with air, which is flowing upward because of some draft. It may be natural draft, it may be forced draft, it may be induced draft. So, what happens at the interface? From the interface of liquid water, as the air is not saturated, if we focus on the mass flux aspect of this cooling tower operation. So, from the interface, as the air is unsaturated, the water gets vaporized, that means it is getting dissolved in the air, right, and moving in the air, okay. But air itself is not getting dissolved in water. So, it is again very close to that interface, it is a diffusion of A through non-diffusing B, where A is the water vapor, B is the air, okay. Think of drying, the same thing happens. Then if you think of any other operations, standard other operations except distillation, everywhere we get the diffusion of A through non-diffusing B. Whereas in case of distillation, you see, we are distillation of benzene A and toluene B, right. We have an interface, this is gas, this is liquid. Now, from the gas phase, toluene will go to the liquid phase, from the liquid phase, benzene will come to the gas phase, because the gas phase will be enriched in more volatile component, that is benzene here, whereas the liquid phase will be enriched in less volatile component, that is toluene for the present system. So, here both A and B are diffusing in the opposite direction, and in the McEpthily domain, right, in McEpthily paradigm, what we will discuss later, we have seen that we can assume an equimolar counter diffusion, right. So, what is the aspect of equimolar counter diffusion? If the two members or two components are the members of the homologous series, which has got the similar properties like latent heat, then the latent heat released because of this liquefaction of a vapor component, right, will be just used to vaporize the same amount of liquid component into gas. So, delta Na and delta Nb, the mutual transfer is nearly equal, and as a consequence we will have the equimolar counter diffusion, right. So, distillation is a process which we can describe approximately by equimolar counter diffusion, where all the other standard mass operations like absorption, humidification, then drying, right, leaching, maybe extraction, everywhere we will have this diffusion of A through non-diffusing B, okay. So, that is why we have chosen the two specific cases to understand those processes very close to the interface, because very close to the interface we will have only the diffusive process. The degree of turbulence or the eddy generation is practically minimized, because close to the interface we have the viscous sublayer. So, first we will discuss the steady state diffusion through a constant area in binary medium. So, this is our general domain, steady state diffusion through a constant area of a binary mixture. First, diffusion of A through non-diffusing B, that is NB equal to 0. And we will consider, or we will derive this equation in terms of partial pressure, because we will now discussing the gas diffusion. So, Na one dimensional, there is no vector, it is a scalar component. So, minus of dAB into this dAB divided by RT into dPA, let us say the direction is Z, okay, minus of dAB by RT dPA dZ plus PA by P into Na plus Nb, that is the general equation. Now, Nb is equal to 0. So, Na 1 minus Pa divided by P is equal to minus of dAB by RT dPA dZ. Now, we consider a domain Z equal to 0, Pa 0, and this is Z equal to L, where it is PAL. So, diffusion of A takes place in this direction, right. So, we will integrate this equation from Z equal to 0 to Z equal to L, considering Na to be constant because it is steady state. So, Na remains constant, right. So, this Na integral dz 0 to L minus of dAB by RT dPA P minus PA into P integral from PA naught to PAL, right. So, minus of or plus of dAB by RT, this P minus PA naught into P minus PAL d of P minus PA divided by P minus PA. So, it is dAB by RT into ln of this P minus PAL divided by P minus PA naught by L. If I write, this becomes Na. So, Na is equal to, you see there will be another P here, dAB into P divided by RTL ln of PBL by PB naught. Why? Because total P is contributed by partial pressures of A and B. So, capital P is equal to PAL plus PBL and also equal to PA naught plus PB naught. Okay. So, P minus PAL equal to PBL, P minus PA naught equal to PB naught. So, you have got this equation. But generally it is our tendency to represent the flux in terms of driving force. And what is the driving force? The difference of partial pressure of A between Z equal to 0 and Z equal to L. So, driving force is PA naught minus PAL. Okay. So, delta of PA is PA naught minus PAL. Now, you see PA naught plus PB naught is equal to PAL plus PBL. So, PA naught minus PAL is equal to PBL minus PB naught. So, what we can write, Na is equal to dAB into P by RTL. Here we can write PA0 minus PAL divided by PBL minus PB0, because this quantity is equal to 1, right, into ln of PBL by PB0. So, further this becomes dAB into P divided by RTL PA0 minus PAL divided by PBM bar. So, where this PBM bar is the log mean of PBL and PB0, right. So, we have the flux expression finally, or alternatively also we can use this expression whatever is required. Okay. Now, once we have got, see, instead of L, if I integrate this equation up to Z, from Z equal to 0 to Z. So, I will get Na equal to dAB into P divided by RTZ into ln of this capital P minus PAZ divided by capital P minus PA0, right. So, Na RT divided by dAB into P into Z, exponential of that gives you this capital, or into this P minus PA0 gives you P minus PAZ, right. So, PAZ is equal to capital P minus PA0 exponential of Na RT dAB into P into Z. So, it is a kind of decay, right, with Z. PAZ will decrease with Z, where PBZ will grow with Z, if Z is the direction of diffusion for A. So, what is the outcome here? This, which is here if we plot P. So, this is PA0, this is PB0, this say it is PAL, and this is PBL. So, we will get this sort of profile. So, A will diffuse in this direction, but immediately the question arises, if we have a gradient of P. So, here we can say that, see, dPB dz is not equal to 0. So, how come NB is equal to 0? Actually, ZB is equal to minus of dBA by RT dPB by dz, and that is non-zero, right. However, NB, that is 0. This can always happen, because NB is equal to JB plus PB divided by P into Na plus NB, right. So, if you calculate back this NB from this profile, you will get NB equal to 0, but JB equal to 0 means what? See, the thing is, the molecules of A is diffusing in this direction. Now, JB is what? JB is the purely diffusive flux. That means that you will observe it, you will observe the same velocity of B if you are moving with molar average velocity. So, if I move with molar average velocity with a reference frame, I will see that B is moving backward, B is moving in this direction. So, JB is not equal to 0, that is why. However, with respect to an absolute reference or fixed reference frame, not absolute, the fixed reference frame, we will see that there is no movement of B. So, though the partial pressure gradient indicates that there is a flux, but that flux is the diffusive flux of B and not the flux NB, right. NB equal to 0, however, JB is not equal to 0. That is the idea. So, that is all about the diffusion of A through non-diffusing B. Now, we will discuss about the diffusion of A through counter diffusing B. It is pretty simple here. So, if diffusion of A is taking place with equimolar counter diffusion of B, then definitely you have Na plus Nb equal to 0. Why? Because Na equal to minus Nb, as it is equimolar and it is a counter diffusion. So, number 2, the case is equimolar counter diffusion of A and B. So, Na is equal to minus of Nb. So, Na plus Nb equal to 0. So, Na, which is minus of dAB dPA dZ by RT, then it will be plus 0, because that term is PA by PB into Na plus Nb, and that is equal to 0. So, you will again integrate in the domain Z equal to 0 to Z equal to L, and here the pressure is PA naught and here the pressure is PAL. So, if you integrate, I will get Na is equal to dAB by RT into PA naught minus PAL, right, very simple, RTL. So, if we do this up to Z, Z equal to 0 to Z, so dAB by RTZ PA0 minus PAZ. So, what do we observe? That Na RT divided by dAB into Z PA naught minus this equal to PAZ. So, it is a linear partial pressure profile, unlike the previous one which was exponential. So, similar will be for PB. So, here is the pressure profile PA naught, here it is PAL, this will be PBL, and this is PB naught. So, A diffuses in this direction, B diffuses in this direction, and this is Z equal to 0 to Z equal to L, right. So, that is the equimolar counter diffusion of A and B. So, we can also have non-equimolar counter diffusion, right, but that we are not going to discuss. So, number 3 is non-equimolar counter diffusion. So, example, let us say we have given the example of diffusion of A through non-diffusing B and also for this counter diffusion. Let us say I have a surface of a catalyst where, or I have a surface of not catalyst, it is a carbon, right, some coal or something, right. Oxygen is coming, we are getting 2CO. The reaction is something like this. Okay. So, here this flux oxygen is Na and this is Nb. So, you can write that Na is equal to minus of Nb by 2. So, this is the relation. Okay. But simply if I think of oxygen giving carbon dioxide upon burning on a solid surface containing of a carbonaceous material, then if I get CO2 here, then Na is equal to minus Nb. It will be a case of equimolar counter diffusion. But here for carbon monoxide, we will have a non-equimolar cases of counter diffusion. So, you see the gas diffusion coefficient DAB for gases, DAB is in the order of 10 to the power minus 4 to 10 to the power minus 5 meter square per second, right, for gas diffusion. Now, the question is, and it is dependent on temperature and pressure. Now, question is how will you measure it? So, measurement of this gas and vapor, that includes two different standard experiments are there. One is called the twin bulb method, another is the Stiffened tubes method. So, those experiments are theoretically important. It is not important from this perspective of understanding the actual experiment and to conduct the experiment, but more importantly we have to understand this just to get the analytical scheme what we follow here to measure the diffusivity, right. And this will be useful in solving some other type of problems, that how to incorporate the flux expressions of diffusion in overall mass balance. So, you see, first we will discuss, this is the measurement of gas phase diffusivity. The first one is twin bulb method. What do? We have two large glass bulbs which are connected by means of a capillary with an valve here, right. This has got a volume V1, this volume is V2, so pressure everywhere is same. Now, here we load A, right. So, at T equal to 0, PA equal to PA0, PB is equal to 0, and here at T equal to 0, PB equal to PB0 prime or PB0 let us say, and PA is equal to PA0, right. And at T, PA and PB are the partial pressures, PA1 and PB1, and at T here it is PA2 and PB2, right. This has got a length L. Now, see, at time t equal to 0, the valve is closed and we open the valve, allow the diffusion, right, for some time, some finite interval of time, and then again close the valve. Then we measure the partial pressure, that is, we have to get the data of PA1 and PA2, because PB1 and PB2 can be obtained upon subtracting PA1 and PA2 from capital P, as we have kept the total pressure constant. Because why? Because if we keep the total two different pressures in the two bulbs, what will happen? There will be bulk flow, right, and that will complicate the situation. So, we have to keep the same pressure in the two bulb, and one with pure, in this one we fill it with pure A, 2 we fill it with pure B. So, now you see V1 into dCA1 dt, it is a case of equimolar counter diffusion. It is equal to A into Na, where A is the area, right, and plus V2, we are going for the balance of A, is A into Na. Now, we should convert it to partial pressure. So, minus of V1 by RT dPA1 dt A into DAB by RTL into PA1 minus PA2, and plus V2 by RT dPA2 dt A into DAB by RTL into PA1 minus PA2. Now, we simply RT cancels out here. So, V1 we cross multiply. So, here we get V1, here we get V2. And now we simply add these two equations. So, minus of ddt of PA1 minus PA2 is equal to dAB into A by L 1 by V1 plus 1 by V2 into PA1 minus PA2. Right. So, that is the, we are reducing it into single equation. We can solve these two equations simultaneously as well by using this Laplace transform and all, right. But here, as our objective is to calculate the diffusivity and we know the pressure from the partial pressure data, so simply we reduce it into a single equation. Our objective is not to predict how these partial pressures are changing with time. So, if I integrate this, you see, if I integrate, so d of PA1 minus PA2 with a minus sign divided by PA1 minus PA2, and here upon integration we will get dAB by L into 1 by V1 plus 1 by V2 into T, right. So, integrate it from PA1, here it is 0, sorry, PA1 equal to PA0 and PA2 equal to 0 to PA1 and PA2. So, it will give you ln of the numerator will be PA0 divided by PA1 minus PA2 is equal to 1 by V1 plus 1 by V2 into dAB into A by L into T, right. So, you know this PA0 and finally, after time t you have measured PA1 and PA2. From there we can calculate the diffusivity, because the volume, measure and the length and the time at which we are closing the valve, that we all know, right. So, this is the twin bulb method for pure gaseous components. So, next is the Stiffened tube method used for volatile components like say chloroform or ethanol. You are measuring the diffusivity of that ethanol vapor or chloroform vapor in here, right, or in any other gas. So, number 2 is Stiffened tube method. What is that? You simply fuse a test tube type thing in a large pipe where the second gas, that is the carrier gas B, is flowing, right. And here you have kept a liquid of A, and this measure is Z, and Z is definitely going to increase with time. Why? Because this liquid will evaporate, and here you see that the gas is moving like this. So, this region is mass transfer will take place through pure diffusion, right. We neglect the end effect here, there will be some vortices and all, but we neglect that effect, and we can neglect that rationally because the diameter of the test tube is much smaller compared to the diameter of this pipe. So, this is a case of equimolar counter diffusion, because here B is non-diffusing, but from here A is diffusing. So, at Z is equal to, or at here, see here, or what is the surface at Z, partial pressure of A is equal to the saturation pressure, and here PA is equal to 0, correct. So, we can write the depletion of Z, we can write an unsteady state equation as say over time t to t plus dt, Z increases from Z to Z plus dz. So, A into rho L, the density of the liquid, divided by its molecular weight into dz dt is the rate of evaporation, and that is equal to Na into A. The A is the area, or let us write small a. A is the area of this tube. Right. Now, Na how we can write? Na we can write as dAb into P RTL ln of P minus PAL divided by P minus PA0. Right. So, here this becomes Z, right, the distance is Z, and at this surface which is PA0, that is PS at and PAL is 0. So, we have A into rho L divided by M dz dt is equal to dAb into P into A divided by RTZ ln of P divided by P minus PS at, which remains constant. This part remains constant. So, this A cancels out, right, and we have Z dz is equal to dAb into P into M divided by RT into rho L into ln of P into P minus PS at, this entire thing into dt, integrate it from 0 to t and integrate it from z0 to z. Right. So, z square minus z0 square will be this entire bracket term into t. So, z changes quadratically with t, right. And from this plot, if I have to measure this z and I know z0, with t I have measured z, right. So, from there I will simply plot z square minus z naught square versus t, and from the slope everything is known except p. So, sorry, except dAb. So, I can solve this diffusivity. PS at we can determine from the Anton's equation of that specific liquid material. Right. So, that is the Stephen's tube method, and you see regarding the gas diffusivity, there are some predictive equation for this gas phase diffusivity, and these equations are mostly based on this kinetic theory and this molecular thermodynamics or molecular perspective. So, one is predictive equation of gas phase diffusivity. So, first one is Chapman Enskog equation. Definitely it has its own limitations. So, dAb is equal to 1.858 into 10 to the power minus 7 into t to the power 3 by 2 1 by ma plus 1 by mb whole to the power half divided by p into rho ab, sigma ab into omega of d, right. So, the sigma ab, basically these are parameters, right. Sigma ab is the characteristic length parameter of the binary mixture, which is sigma a plus sigma b by 2. These are molecular parameters, and omega d is the collision integral, which is a function of kT divided by epsilon AB, where epsilon AB is the interaction energies. So, from this we can calculate. Additionally, we have this another equation, Fuller, Schechler and Giddings. This is less accurate compared to Chapman and Cox, so which states that DAB is equal to 1.0133 into 10 to the power minus 7 T to the power 3 by 2 divided by P, then sigma of VA to the power 1/3 plus sigma of VB to the power 1/3 whole square into 1 by MA plus 1 by MB whole to the power half, right, and that is in meter square, both are in meter square per second, where sigma of V for each component can be estimated adding the atomic diffusion volume data available for the different structural groups and all. So, for individual components we have to add the structural groups, diffusive volumes and all, so to get this. So, what is important to note from these two equations, that is the diffusivity is temperature dependence and pressure dependence. So, basically what we have to remember finally from this equation is that DAB is proportional to T to the power 3 by 2 and inversely proportional to pressure. So, that is the important point, right. Now, we can think of a question where we say that okay, we have an equimolar counter diffusion, diffusion of A through non-diffusing B. So, DAB into P divided by RTL into ln of P minus PAL divided by P minus PBL, PA0, right. So, how this flux is going to change if I change the temperature from T1 to T2 and pressure from P1 to P2. So, you see that we can write Na1 by Na2, the total pressure whenever I am changing this, it is basically the what? The mole fraction. You can write this term as 1 minus PAL by P divided by 1 minus PA0 by P. So, that is going to remain unchanged no matter whether we are changing the pressure and temperature, right. So, these are basically the mole fractions. So, it is dependent on DAB into P divided by T. So, DAB into DAB1 P1 by T1 divided by DAB2 P2 by T2, right. So, DAB is now DAB0 into T to the power T1 to the power 3 by 2 by P1 into P1 divided by T1 and total divided by DAB0 into T2 to the power 3 by 2 by P2 into P2 divided by T2. So, basically P1 cancels out, DAB0 cancels out, P2 cancels out, and T1 to the power 3 by 2 divided by T1 will give you T1 to the power half, right, in the numerator. So, it is finally giving you T1 divided by T2 under root. So, from this you have to calculate the ratio of these two fluxes where we have changed the temperature and pressure. So, what is important to note that it is independent of pressure, right. So, similarly you can check it out in case of equimolar counter diffusion. So, that is about the gas phase diffusion. In the next session we will start the molecular diffusion aspects of the liquid and its determination procedure, and then the diffusion of a component through variable cross sectional area. Thank you.